Hi there. Welcome to Sample Space. This is a show where we try to explore tools, thoughts, and techniques from the world of machine learning that deserve some extra attention. My name is Vincent, and I will be your host. In this episode, I'll be talking to Leland McInnes, who might be most well known for creating UMAP. This is a technique and a Python library that really makes it a lot easier to visualize clusters of lots of data points. You may have seen some of these when people have embeddings and they try to see where clusters are. 9 times out of 10, if you see one of those cluster charts, it's UMAP. Leland isn't just known for UMAP though, he actually wrote a bunch of packages. PyNNDescent is one, HDBScan, and there's also a few tools that help you make pretty charts using UMAP. So I thought it was interesting to talk to him, not just because he's working on some new tools that I think are pretty exciting, but also because I was interested in Leland's perspective. What drives someone to make all of these tools, and what can be learned for everyone else out there? I found this conversation to be extremely interesting, and I think you'll also really like it. So, hi Leland.
Hi, how's it going?
Hi. Good. It's getting to summer here. Because are you based? Because you were from New Zealand originally, I think.
That's correct.
Right?
Ottawa, Canada now, though, so we're just starting to have spring. The tulips are just starting to bloom.
There you go. Yeah, and like humid season is starting here in the Netherlands, and yeah, okay. So good things are coming. Like we're out of winter, and all that stuff is great. But we are here today to talk about some software that you've made. Because you've got a pretty interesting resume, if only on the GitHub side of things, because you contributed to HDBScan and to UMAP and to PyNNDescent and like a whole bunch of packages. And my impression is that UMAP is one of those things where people have seen the pictures, like the blobs, they kind of appear in a neat little cluster, but it's always tricky to me, at least, how to explain what UMAP does. Is this something you've battled with as well? Like you have pretty pictures, but then people ask the follow-up question, like, "Hey, how does UMAP work?"
I think it's a very challenging question because I think the explanation really depends on the audience, and so I need to find different ways to explain it to different audiences who are looking to get different things out of it. So there's a lot of different ways one can explain it. Some are definitely more mathematical. Those are usually for the mathematicians that have a similar mathematical background to me. I've explained it to those people in terms that I think are in the paper that a lot of people complain about because it's too technical, but to them it seems straightforward and obvious.
And what kind of terms would that be? Would that be like topology?
Yeah, sort of algebraic topology and things like that, where, that's just a language where it's easy to describe these sorts of structures that you're interested in finding and how to access them and compute with them. And so it's a very natural language if you know that language. But if you don't know that language, then it's extremely opaque and unhelpful.
Yeah, so I could to kind of make a UMAP joke, it is kind of a cluster of its own, I can imagine, that kind of niche, to put it that way. But okay, you've got the mathematicians, and they have, I suppose, their jargon, and they want to have things very formal. And then you've got what are some other crowds that you've interacted with?
So the computer scientists just want the mechanics of it, like what are the computational steps that I need to do. So they don't care about the algebraic topology side. They're like, a graph, you're going to build a graph, okay, and then you're going to lay that graph out in a graph layout algorithm. That's what you're doing, and the answer is yes, that is.
So the mathematicians, they prefer to understand the formal why, and I guess the computer scientists are a little bit more concerned with what and when, like the order of steps in which things happen.
Yep,
I guess.
Yeah, and then like the practical end users who don't necessarily care about the internals so much, they just want to know what it's doing, as in, when I get an output, what can I trust, what can I not, what matters, what counts.
So I see. Yeah. So people use UMAP to get something in a 2-dimensional representation, and then you can plot that, and you can add colors if you like. And then people look at it and wonder, well, what do these blobs mean?
Exactly.
Can I get meaning out of it? And yeah.
Kind of so it does the process of reducing anything down to a visualizable thing from a very high dimensional starting point inevitably has to make compromises. You can't You can't take all the information in this giant, complex, high-dimensional data set and somehow squash it into something you can visualize and not lose something in the process. And so the question is, what are you going to lose? What sacrifices are you going to make? And all the different algorithms that exist just have slightly different choices about what they're going to sacrifice. What are we going to give up to get there? And that's kind of the sorts of things that people want to know, because UMAP is going to push towards making things into clusters. That's kind of what it was designed for. It's interested in topological structure, so that's at the very base level cluster structure, and then sort of higher topological things like loops and strands and things like that, and on up. And so it's very tuned towards doing those sorts of things, whereas more traditional classical thing like principal component analysis, that wants to capture the overall variation in the data, as much of the variation in the data as possible. So the things you can trust about a plot given to you by PCA are very different than things you can trust about a plot given to you by UMAP.
So one thing I can imagine is that people do understand that if you have something in an embedding, let's say 300 dimensions, and you turn that into a two-dimensional thing, that you do lose something, right? That feels plausible. One thing I do kind of wonder is, have you also spoken to people who want to then do it in 3 dimensions? Because I can imagine you would hit the same problem. It's just that you've got 3 dimensions instead of 2. And going from 300 to 3 is still like a lot of information loss compared to 300 to 2. But is there a use case for 3D UMAP reductions as well?
Absolutely. They get used for various use cases. I think the biggest reason that you don't see them as often is that people are often using it for visualization, as you say, and there are costs to going to 3D for visualization. Like, to be able to visualize something in 3D, you need an interactive plot so you can like rotate around and move through. And that's a big cost to how easy it is to visualize. And so you need to be getting enough benefit out of adding that extra dimension to make it worth your while. But you can do 3, you can do 5, 7, 10, whatever you like. And there are reasons for doing these.
Would I be correct in saying that if you want to do 3 dimensions, you almost have to do some JavaScript stuff to get it to run in the browser neatly? Whereas 2 dimensions, well, you can actually print that on a piece of paper if you wanted to. Is that kind of the difference? Or
yeah. You can print out a 2D plot and have something to look at, and you're done. But a 3D plot, I guess maybe with some of the virtual reality things out there now, you could make something work that feels like actually 3D, but it's not something that just neatly goes on a piece of paper, or for that matter, on a flat screen, without having something more.
So one thing I wonder, because you did mention that I thought I was going to mention 3 dimensions because that's kind of an edge case there, but then you went ahead and said, "Oh, there's also 4 dimensions." I got to ask, like, could you give an example of a use case to use 4 dimensions? Would I then imagine 2 2D plots where people can maybe interface with, or like?
I mean, the use case for me for that is for clustering. So if I use UMAP, that, as I say, tends to emphasize or contract in those cluster structures, which can be otherwise hard to deal with. Most clustering algorithms don't work very well on high-dimensional data. If you use UMAP to reduce it and then cluster it, you can actually get very good clusterings out, just classical clustering. And there's no, now Gotcha. I'm not visualizing. There's no need to look at it anymore. I can use however many dimensions does the job.
Gotcha. So it's UMAP can also be seen as a pre-processing step in that sense. Like, a lot of people know it for its visualization capacity, but if you are mainly interested in clustering, it's a pretty decent way to also pre-process.
Yeah. And I mean, a use case I've seen that was not something I would have ever expected. There's a digital artist, Refik Anadol, and he does very impressive visual digital art works, and he uses UMAP in some of his work. So I'd never expected to end up in having any of my work used in like actual graphical art. He had an exhibition at the Museum of Modern Art in New York. And so
No.
he used 7-dimensional reduction. And so the first 3 dimensions were used for a 3D spatial coordinates. The second 3 dimensions were used for color coordinates in color space.
Oh, cool.
And an extra
cool.
dimension was used for time, so he would like rotate through that, so that the colors would rotate through the 3-dimensional spatial thing.
So how did you hear about this? Like, did the artist also reach out to you, or did like a buddy of you send you a text message at some point going, "Hey, friend, I believe you're in the moment with some of your work"? Because that's not like I would not have expected that, to be honest. I'm super cool, of course, right? But like, I'd never expected
Absolutely.
that one.
I encountered his work online. He's been in touch, and we have chatted occasionally. I mean, he is
Cool.
super busy and super popular. So, I mean, it's been an honor to get to chat with him at all. And so, yeah, once I heard that he was using UMAP at all, I've pretty much just followed what he does on a regular basis, and yeah, it's been very interesting.
I'm gonna do my best to include his work in the show notes. That's a very nice anecdote. So I wanted to discuss interesting applications, and in my mind, you would say something like, I don't know, biology, right? Like something like that would have been sort of on the list. Um, I do want to ask further, though. So definitely the art is a thing I didn't expect, but looking back at UMAP and like, you're on Twitter and you probably see some pictures pop up of people's work. Like, have there also been other sort of unexpected or interesting applications in hindsight when you look back at it?
Yeah, I mean, it got used a bunch during the pandemic for things related to looking at different variants of uh, coronavirus, which was not a thing that I personally would have expected at all. And
So what goes into the clustering algorithm then? So you say virus, but I'm assuming that's DNA information or something like that, or
so this is where we're getting into the biology of the papers that I don't have the background to speak
right?
on. There was data that they had that they were feeding in, and it was clustering various strains of the virus. So
Gotcha.
it was both unexpected and expected. I mean, in my original work, uh, when I was first developing some of the ideas for this, I was actually looking at clustering computer malware virus. So
All sorts of viruses.
yeah, so apparently it eventually came full circle. But yeah,
Oh.
and then another thing that I've seen is clustering of vocalizations, so audio. So there was some great work by Tim Sainberg, who was looking at bird vocalizations. So you can cluster it into syllables with things like UMAP, and then you look at the sequencing of the syllables and compare that to sequencing of syllables in human speech. And there were apparently interesting like similarities and differences in that. And Tim went ahead and wrote a parametric version of UMAP that uses neural networks to do a bunch of stuff with it that he contributed back. So that's been really amazing. And bringing it back to the art world, Kyle MacDonald, a different artist, used UMAP in a bunch of his work. One of them was in clustering whale song for a giant like installation art piece that he did with another artist. And like UMAP was not the display element there. UMAP was a thing used in his working process to get towards the actual piece that he did. It was just a part of the clustering of whale song, so you could get different syllables of the whale song out and use that in some of the representation in the piece.
One thing that's interesting here, as I listen to some of these stories, is that it seems like there's something general about UMAP in that there's a big data set and one doesn't know the story in that data. But if we had clusters at our disposal, that might help with the interpretation. And it's that UMAP tends to help out with. If only for the visualization aspect, but also to aid with the clustering. It's kind of like that's the magic Lego piece where UMAP seems to sort of be the center of.
Yeah, the way I think of it is that UMAP is a tool to help you ask questions about your data. It's not a tool necessarily for getting to the final answers. it's a tool for finding the better questions to ask. So
Yeah, something.
it's a
Yeah,
way to get access. I mean, otherwise, how do you deal with a really large data set? You've got to do something to find something interesting, some structure, something to find in it before you can even ask sensible questions about it. And scrolling through a giant pile of numbers is not the way. Visualization is definitely a go-to choice, and there's lots of different ways of doing visualization. Don't get me wrong; like UMAP is an option. I would use as many as I could, but it's a way to get access to some of the structure in the data that you can ask better questions.
yeah. That reminds me of Hadley Wickham. He's mostly known for his work in the R land, but he had this one nice quote where algorithms can scale, but they typically don't surprise you. Visualizations are very hard to scale, but when you actually get them to work, they can surprise you. And that's kind of the interesting thing you want to go for with visualization. And UMAP kind of helps with the scaling there, I guess. That's maybe also a way of looking at it. It makes visualization just a little bit more scalable.
Yeah, it scales visualization and it brings visualization to data sets that otherwise wouldn't have it. I mean, in the modern era where we have neural networks that can embed images and audio and text, uh,
And everything
everything
in the
under the
kitchen
sun.
sink.
Yeah,
And
yeah,
yeah,
yeah.
yeah.
Now I can visualize a giant corpus of text. Now I can visualize a trove of images. Not a single image, but millions of images. How do I know what a data set of millions of images looks like?
Yeah, that's true. Yeah, you're not going to get there by just staring at pixel values. Like you need something more. One thing I wonder, and this is more of a small technical question. UMAP that supports dense data, but does it support sparse data structures as well?
It does, yeah. That was a specific feature that I very deliberately worked on. It's useful for a bunch of use cases, but I think has been it's less widely used by I would say in general, but very powerful.
So I remember using UMAP on a sparse data set, and I'm always like, part of me always is so happy when I see it actually is implemented on sparse data because there are a bunch of these like tiny little use cases that are really hard to solve otherwise. Is this something you've noticed as well in general that like sparse data is a bit underappreciated at times?
Absolutely. I don't know why. It is it's a good first pass at a lot of different problems. I mean, the main one I would think of is dealing with text. Bag of words or TF-IDF should not be dismissed as I know we have neural nets now, but go with something simple first, and those are inevitably going to give you sparse data. So
Yeah, no,
you need something that works with those.
yeah, and like scikit-learn still is pretty good at adding more and more support for this sparse stuff. Like recently, k-means can do sparse data structures now, which is super cool. Part of it is there a solver that can handle it? I mean, there are like good technical reasons why handling sparse data is not necessarily super easy, but it is always a bit of a bummer that if you want to get sparse stuff to work inside of PyTorch and TensorFlow, you actually have to really go deep into the docs because just not a whole lot of people are doing it.
Yeah, I mean, the end result is you've got to actually be familiar with the internals of sparse data structure representations because there's a lot of them, in fact, and
Yeah,
moving between them is important if for different use cases.
yeah, I was looking at the docs this morning. I think SciPy has like 7 or 8 different representations, and one of them is really good for retrieving rows, and the other one's great for matrix multiplication, and the other one's great for math, but then has more memory, and et cetera, et cetera, et cetera, et cetera. You got to know what you're doing. One thing I kind of want to pivot now because there's a list of things I would like to talk to you about. We've discussed UMAP now, but technically UMAP is one package, and you've made a few of them. One of which I think eventually made its way into scikit-learn, which is called HDBScan. Um, and one thing I thought might be fun is to briefly talk about what it does. But I believe there's also a pretty interesting anecdote in how it actually ended up in scikit-learn, which I think would be a shame not to mention. So, um, HDB scan, that's something you've also worked on. Like, if you were to explain it, what does it do?
So HDBScan is a density-based clustering algorithm. So the algorithm was actually originally developed by some of the same people who made the original DBScan algorithm, which is certainly a very popular classical clustering algorithm by this point. And they wrote a paper on it, and it looked like a very promising clustering algorithm to me. So I tried to write an implementation for Python. And the what does it do? It's trying to extract dense regions, contiguous dense regions, out of a data set. So it's trying to find areas where there's lots of data that's separated from the rest of the data by sparsely populated regions. And it picks those out very well. So it's kind of like, if you're familiar with DBScan clustering, as I say, that's pretty old school now, I guess, in the world of machine learning, that apparently 5 years is a long time. It's like that, but it is adaptive to the density. So DBScan, you need to pick a distance parameter, and HDBScan, you don't need to do that. It'll do different variable density and so on.
And from the implementation perspective, I think, if I recall correctly, one thing it does that's kind of interesting, because not a lot of models do that, it does clustering, but it also does outlier detection all in one go. Like, I remember using it the first time, and -1, if it predicts that's in scikit-learn land, that means outlier. And this is kind of an algorithm that does clustering and outlier detection in one swoop, which not a lot of approaches do, but this one does, right?
Yes, it does. So this is, I would describe it as the difference between clustering and partitioning. And a lot of algorithms that are called clustering algorithms are partitioning algorithms, where the goal is to simply split the data up into piles. Whereas, to my mind, when I use the word clustering, I want it to mean pull out important piles, and if there's other stuff that doesn't fit in any particular pile, just leave that alone. And so those are your outliers.
There's a lot of subtlety there. It's actually very true. Gotta ask, like, were there any surprising use cases for that? Because that package has been out there for like almost a decade as well. Like that work originally. So there's been also like UMAP is also pretty old at this point, but there's like a decade of people playing around with it. Did you get any interesting use cases here? Like, did HDBScan get featured in like the Royal Academy of some other museum, or?
No, not that I'm aware of, but it has
Right.
certainly been pretty widely used. It crops up in a lot of places. Probably the most prominent use right now, actually, is in topic modeling, which used to be latent
Ah,
Dirichlet allocation was the standard method, but there's been some newer approaches, Top2Vec and BERT, that use neural embedding models, BERT and such like, to process the text, and then topics are clusters within that. So that handles short documents far better than something like latent Dirichlet. And it is probably the go-to choice for most of the packages that do that kind of clustering.
and then okay, and I think the implementation that people are using these days now, that will be the implementation that's in scikit-learn.
Probably
Right.
it is now actually in scikit-learn proper, and that was a long journey.
So could you maybe shine a little bit of light there? Like, I'm asking because I know part of the anecdote, and I think it's an interesting story, but I do think it's a story people might need to hear, because um, you started working on this plugin package, and I believe it was one of the first packages that made it to like the scikit-learn contrib region of GitHub, and then eventually it went into scikit-learn proper. But that took how long?
Uh, Almost a decade. It's been a
So
long time. So this was one of the first times I actually wrote a Python anything and put it somewhere external. So I, with a small group of people, put together a very basic implementation of it way back in 2015, I guess. And I once it got to a reasonable point, I was like, oh well, we were using the scikit-learn API because that seemed like the obvious thing to do. So I was like, oh, I should contribute this to scikit-learn. So I put in a pull request to add it to scikit-learn, and that was rejected. So that was my first pull request on an open source project of any kind, was to add HDBScan to scikit-learn, and it was rejected. So that was disappointing. But the rejection was a very reasonable one, and that is that scikit-learn only really wants popular, well-established algorithms. They can't include everything under the sun, just for reasonable reasons. And at that time, HDBScan was very new, and it didn't have enough popular usage or citations in the literature to justify its inclusion. So they very kindly said, "Look, we can't do this right now. You should make this your own package. You can use the scikit-learn API, you can publicize it, and see where you go from there. And if it gets popular, maybe time will come. It can get included." And so I made it into a package, started putting stuff together for it. And then, as you say, I heard from the scikit-learn maintainers, suggested this new scikit-learn contrib. So it got moved to that space, and it lived there for a long time. And then the last few years, somebody else actually went to the trouble of porting it and getting it into scikit-learn proper.
So how did that happen, actually? Was it that the scikit-learn people at some point said, well, actually, now we see it in all the papers, we probably want to get it in? Or was it like someone external that went to the scikit-learn people and said, well, actually, I've been using it for a while. Like, how does that mechanic work?
So actually, I'm pretty sure that was me chatting with some people at SciPy conferences, I believe. So Andreas Mueller and
Yeah, yeah,
Gail Veracqua show up at these conferences, and I chatted with each of them at various times, and pointed out it's pretty popular now. Can we get there?
Should it? Yeah. Oh, interesting. No, so there's always a human element to all of this, of course. Like, because people have schedules and they can't do everything in one go. And sometimes it can help to just meet people face to face to be reminded of a thing that happened 10 years ago, which I think is a story with HDBScan.
Absolutely.
Like,
And to be honest, by the time it reached a point where that it was ready to go in, I didn't have time anymore to do the port, because I mean, it was written as a package that was scikit-learn compatible, but actually fitting it in to the modern scikit-learn by that point as its own component is a non-trivial amount of work.
and is that because it had to be translated to Python or something like that?
It
Or
was already in Python. It's just gluing it together with all the internals of scikit-learn, going through and meeting all the required coding standards. It was
oh,
mostly up to that, but there's a lot of just fiddly detail work to actually get all the pieces in place. And I, by
yeah,
that
makes
point, didn't
sense.
have that time. So somebody else took that on, which was wonderful.
Cool. Okay. Interesting. Like, what's interesting here is this took about 10 years to finally get in, but maybe the most interesting stories is that after 10 years, something can actually still go in. Like, that's also kind of a fun, unique thing. Like, if an algorithm just proves useful, scikit-learn is definitely going to be eager, I think. So it's actually a pretty cool story that after 10 years, still went ahead with it. Kind of moving on, because this is the second package that I think you could be well known for, and I think there's actually one other one called PyNNDescent. And now the reason why I think that is interesting is because we kind of live in the world now where there are lots of approximate nearest neighbor algorithms and even databases and lots of VC money in that field. People want to like do nearest neighbor lookup for vectors. But your original PyNNDescent has an interesting sort of niche use case that I do think is interesting to maybe talk about just a little bit. So, if you would, what's the easiest way to explain PyNNDescent? It does vector k-nearest neighbor retrieval, but it's a little bit different, I think.
Yeah, well, I mean, it's targeted towards some pretty specific use cases in some ways. So it's not meant to be a vector database. It doesn't have all the infrastructure built around it that a vector database would want to have. It's designed to be just an in-memory store that still has fast nearest neighbor lookup. Also, just constructing all points k nearest neighbor graph out of a vector dataset as efficiently as possible. That's its other main use case. But also, I wanted something that could handle all the different kinds of data and different distance metrics. And that is, I guess, some of the other aspects that really motivated me to write my own package.
Because you wrote the whole thing in Numba, if I recall correctly, right? So there's this just-in-time compiler trick you can do in Python via Numba, so that can keep things kind of fast. And I was playing around with it the other day, and I think also the use case here was because it's in Numba, it's pretty easy to also come up with your own cost function, which I think is what's happening here as well, right?
Yeah. So a lot of the vector databases will say, "Oh, you want cosine distance because that's what most of the neural networks use, or inner product distance." Fine, we can do that. Maybe they support Euclidean, and often that's
and those are
about
the
it.
three.
Yeah, but
yeah, those are the usual suspects. Yes.
there's a lot more ways to actually measure distance between objects, and it would be nice if something could support more of them. And so PyNNDescent out of the box supports a pretty large set of distances, but because of the way Numba works, because it does the just-in-time compiling, you can write your own measure of distance, and as long as it's compilable by Numba, you can hand that in on the fly in your notebook, and it'll run very fast, which is hard to do
And
otherwise.
well, and also here, which is like I think PyNNDescent also does something that a lot of these other providers don't do, which again is sparse data sets. That's a reason that I've used it in the past. It's again one of these little details where it doesn't have to be a full-fledged database, but it's still reachable from Python, and it integrates very nicely with the rest of the stack. So with that in mind, PyNNDescent, if only for rapid prototyping, I've always found like a pretty convenient tool. Um, Another aspect of this, which is something we talked about earlier, um, you can kind of use it for k-nearest-neighbor types of algorithms. And there's something interesting about that as well. K-nearest-neighbor algorithms are a little bit out of fashion these days. But one aspect of that is that you can look at data as the model. That's like a thing, like a theme I have in my mind. Maybe so. We've talked about this before, so we're just going to sort of repeat the conversation. So, like, what's with that in mind? Like, what's the cool use case for PyNNDescent when we think about k-nearest-neighbors in your mind?
Right. So, I mean, if you're doing a k-nearest-neighbor classifier, you can use that in scikit-learn. There's a k-nearest-neighbor classifier model already there, but they refactored scikit-learn a while ago so that most of the tools that have to do k-nearest-neighbor type computations can take a pluggable piece. And as long as you have a piece that meets certain API requirements, it can do it. So in scikit-learn, there's nearest neighbor algorithms that they have that are exact nearest neighbor algorithms. They're slower, shall we say, but you can use PyNNDescent as a plugin in place of those, and have the approximate nearest neighbor search work for k-nearest neighbor classifiers. And so that's very powerful. And I think k-nearest neighbor classifiers are underrated. As you say, there's data as a model. I like that phrasing of it. To me, I think of it as it's a magically editable model. So we live in a world now where there's like legal requirements, right to privacy, things like that. Maybe you have some requirements that some of the data that you had trained your model on needs to be redacted for those purposes. Do you need to retrain your model from scratch now so that it no longer contains that data? I mean, how else do you prove that your model hasn't memorized some of that data that you need to officially remove? Well, with a KNN classifier, you just delete those data points and you're done. There's no model retraining to be done. If you are looking through your data and you find that some of your labels are wrong, which is a thing I know you're familiar with.
Yeah, a lot of people come up to me and say, our label quality is immaculate, and that's always a challenge accepted moment because it usually never is.
Yeah. So, I mean, if you've already built your model, how do you deal with the fact that you suddenly realize that, oh, some of my data points were mislabeled? Well, if it's a KNN classifier, I just edit the label in the data. I'm done. Model updated. Do you need to fine tune a model with some new data that you got that would make it better? Or just throw all that new data in the vector database or whatever you're using.
And done.
Done.
Yeah. No, so and also there's something about even when you do a KNN retrieval, right? Like you get 20 items back. There's also a big interpretability win, I would also say. So if someone were to ask you, like, "Hey, why did we make this prediction?" You can just kind of say, "Well, these are the most, I don't know, doing car prices. These are the most similar cars," and kind of look at it and say, "Okay, fair enough." And if any of those cars don't seem to match well, then okay, you also understand why.
Yeah.
So there's all sorts of fun interpretability things there, I suppose. Like, but why would you think KNN has sort of lost favor a bit? Like, I understand that we've had the ImageNet moment, and neural networks are kind of in fashion, but it also felt like KNN classifications. I don't know. Was it maybe that it's too simple of a model? Is that maybe something that played into this? Like, I don't know if you've got a perspective here.
Yeah. So I think, I mean, these things come and go from fashion, right? There was a time when neural networks were very out of fashion, and there were reasons for that back in the day. I think was that they didn't at that time perform as well as a lot of other sort of standard things like random forest and gradient boosted trees. They've definitely improved since then. We got new hardware, new algorithms, and everything works much better. And I think with KNN classifiers, the problem essentially was that, well, the model has to be huge because I have to store all the data. And nearest neighbor lookups are really expensive. So computationally, it took a long time. I mean, it did back when they became unpopular. But we live in a different world now. Nearest neighbor lookups, at least approximate nearest neighbor lookups, are something we're really good at now. There's excellent algorithms for this. It's very fast. So that's no longer a problem. And the model still has to have all the data. So it's a really big model. But have you seen the latest neural network models that you have to download? Big models are not a problem anymore.
Yeah. And like I can imagine back in the day, people had this nice idea of a model is also kind of like a compression algorithm. Like it really tries to maybe reduce it down. But disk is also becoming cheaper. Memory is becoming cheaper. I saw at Hetzner you can get a 32 gigabyte RAM like VM with 12 cores for like $40 a month now. So like a lot of that stuff has moved on since then. And then you can wonder, well, maybe some of those older approaches are actually more viable now. And it's interesting to sort of look at that and wonder if we can celebrate KNNs a bit more. One thing I wonder maybe that's related to this, like if you're going to retrieve similar items, you still have to solve when is something similar? And they kind of get back at the embedding bit, like when is an embedding a good embedding? And you might have to retrain the embeddings and sort of stuff in that realm. Is that like an issue you've seen as well?
So a problem I'm sort of interested in working on for a variety of different purposes is being able to be adaptive in how many nearest neighbors one returns. So if I ask for nearest neighbors, how many things are actually close versus just returning the top K? So I'd like to be able to return maybe just the top 3 if there's only 3 things that are close and the next 7 things are too far away, or the top 10 if all those 10 things are close. This is not a standard thing, and the trick to doing that is you have to manage to vary your notion of closeness throughout the space. So you have to be able to model what it means to be close all across the data space, which is an interesting problem and related to UMAP, it turns out. That's one of the first steps in UMAP is, I need to reset my notion of distance throughout the space based on the local density of the data. So you can play similar games, and you have to be a little more, requires a little more finesse about it, but you can play similar games and try and do similar things for working with KDearestNeighbors.
But then you also kind of get back to that outlier argument, right? Like, so suppose that I'm predicting car prices. You can say, well, fetch me the most relevant cars to the car I've got now. And then for one type of car, you can say, well, these are 90 cars that all look very similar. Fair enough. For this car, there's only 5 other cars. But you can also say something like, that's not a car, that's a bike or a boat or a Batmobile or something along those lines. We have nothing that looks like it. Would that also be kind of become part of the query?
That would certainly be the goal. If what you want to do is return a variable number of nearest neighbors, which you're going to then use in your classification, if you return 0 nearest neighbors, you should just refuse to predict for that point.
Yeah, raise a won't predict flag or something like that.
Because it's clearly outside the range of what you expect from the training data you've seen. And so a robust K-nearest neighbor classifier that can be adaptive like that, I think that would be a very powerful thing to have. So that's definitely something I'm working on currently, and hopefully maybe there'll be a library for that in a year, 6 months, something.
So there's a lot of things about this are pretty interesting, because it's we've talked about UMAP, we've talked about HDBScan, we've talked about PyNNDescent, and they all seem pretty related. And we're now talking about something new that also feels pretty related. So it's like a planetary system where all these sort of planets revolve around the sun. It kind of feels like there's ideas that you've got in your mind, and packages sort of come out of that. Would you argue that that's because you've just exposed yourself to a certain set of problems, or like because it is interesting to see, right? Not everyone writes so many packages that do seem to do something specific, but also seem so related.
I'm always just trying to solve the next problem, to be honest. So HDBScan, as I said, was my first open source anything, to be honest. And that was all about solving clustering, which was a problem I'd run into at the time. But then the difficulty we had was, well, it didn't work very well on high dimensional data. So I need to solve that. So now I need to be able to do dimension reduction so I can run HDBScan in a way that's going to preserve as much of that cluster structure as possible. And out of that sort of line of thinking falls out UMAP. But then to build both UMAP and HDBScan, a primitive that's required is building a K-nearest neighbor graph. Well, I need to be able to do that as fast as possible. So I end up building tools to be able to do that. And on it goes. So now I'm interested in K-nearest neighbor classification, K-nearest neighbor type algorithms. So K-nearest neighbor classification comes up. It looks like an interesting option, but what do I need to make it better? Well, I can steal ideas from some of the other bits and pieces that I've been working on and try and feed into that. So there's always different pieces of the problem that I'm busy trying to solve. So another recent package I worked on was data map plot, which is dealing with the fact that UMAP produces these visualizations, but people actually still have to do a bunch of work to visualize it and visualize it well. And it turns out that if you can make it really easy for people to do that, there's more uptake. Users are more happy with it if you can make good outputs easy to produce. And so that was just I need to make it easier for some of my users to be able to get to this point. So I better write a tool that solves that. And so yeah, it's always just what's the next problem that comes up for me when I'm trying to use the tools myself and trying to help other people make use of them better.
So it's partially a story of you're exposed to new problems all the time, and that sort of helps you motivate the next tool. But it's also kind of convenient that you've got these tools that you've built in your backpack that you can go ahead and reuse. That's also something that you notice.
Yeah. Yep. I mean, I guess you can start sticking like grand narratives through a whole bunch of the tools that I've built and worked on, where the goal really is just to be able to explore data sets. That's clustering is a way to do that. UMAP visualization.
That's the overarching theme of the book, you could say.
Yeah,
like every chapter is a new package, but the overarching theme is there's a big data set. What's in it? I don't know the story of it. And for that, you need some tools, and that's kind of the domain where you're trying to help.
Yep, that's pretty much it.
So one thing I do want to touch on before we wrap up is I'm sure that you write tools, you do it for yourself, and that's great. But eventually, some of them actually become quite popular. And I could be mistaken, but I wouldn't be that surprised if UMAP has like almost 1 million downloads a month now. It's definitely fair to say it's up there in the top 100 or so of data science packages, easy. And from that, I'm sure there's lessons that you've learned or things you didn't expect, not necessarily how the package is used, but just what it's like to be a maintainer of something like this, something that's that popular. Like, are there some pros and cons you've learned about being a maintainer of something this big?
Well, probably one of the biggest pros for it is that I've had a lot of help from a lot of people. Because it's a popular package, so a lot of people reach out to help. So I mentioned Tim Sainberg, who was doing bird vocalization, wrote a parametric UMAP that uses neural networks. So, that's fantastic. Quite recently, Keras got a major update to Keras 3, and that meant that the Keras components of parametric UMAP were no longer working with Keras 3. Francois Cholet reached out and offered to do the port and fix. I was like, okay, I sold.
So for context, Francois Soleil is the chief maintainer of Keras, I believe,
Yes.
is like what he's most well known for. But the chief maintainer of Keras reached out to do that work, so you didn't have to, basically.
Absolutely. So yeah,
Nice.
that I mean, to have people of that caliber do anything to help you is something that you just there's no comparison. Like the quality
That
of
is
and
cool.
number of people that have reached out and helped with these packages is amazing, and I'm hugely thankful for all the people who have put in any effort or time at all in this. I need all of them, and it's been really helpful, and the popularity makes that much more possible.
And I can also imagine it's a good motivation to keep on maintaining a project. Like the learning rate is still high for you as the maintainer because there's all these people coming up with new ideas to sort of make it better or serve a different purposes as well.
Yeah, yep, absolutely.
Sweet. Anything that you've learned though, when it comes to sort of maintaining some of these larger packages? Some of the people listening might also be maintaining a package. What's if you were to sort of have a big lesson that you've learned looking back? What would it be?
uh, Documentation. Documentation matters. That is my big lesson, and I lucked into this. So at the time I was writing HDBScan, I went to PyCon and went to a tutorial by Eric Holscher, who is the person behind Read the Docs website, which hosts documentation for
Tons, yeah,
all the
tons and
Python
tons of
packages.
documents. Yeah.
And so it was a tutorial on writing Sphinx documentation, and he was giving it, and I sat through that tutorial, which was an excellent tutorial, and I used it to get me started writing documentation for HDBScan, following the templates and the what kind of documentation you need to write that he laid out, and I ended up with, I felt, pretty decent documentation for HDBScan, and I think that made it dramatically more popular at the time because, and I've had that feedback from a lot of people that the documentation was great and it really helped. And so thereafter, I've had to live up to that standard of documentation for other packages I write, and I've had continued to have the same feedback. The documentation made all the difference. Just having it there to be able to document how to do all these things and readily accessible, clear explanations of how the algorithms work, all these sorts of things, these make a huge difference to people wanting to pick up and make use of them.
And if there's anything specific about like doing documentation that feels that might be overlooked, like is there any? Like, I can imagine if you've never written docs before, like there's lots of stuff you could be working on. There's the API docs, etc. But is there any sort of particular guide that you feel that like, oh, that's usually missing from an open source package, or if people focused on this, the docs would immediately be better?
I
Was there anything for you specifically that you remember, like, ah, if I just make sure that that's in the docs, that makes the biggest difference?
If you can, if you're working with a new algorithm, if you have a how it works section that is
Hmm.
well written for somebody who doesn't necessarily need to dig into all the technical details. So it's very different than a paper. Writing a paper on how an algorithm works, you write very technically. So, just a casual discussion of how it works. And the other thing is a quick quick start guide tutorial to using the thing. Those are the two things that I feel need to be there. The amount of stuff that I've seen that is somebody copying and pasting code straight out of the first 5 lines of the first tutorial on how to use the package as getting up and running that's a huge amount of stuff. People want to know how to use this thing, and I'd like to get to that point as quickly as possible. And if you have a quick start guide that gets you running it on some data in copy and pastable code, that makes a huge difference, because people actually just do that and then modify the code, insert their own data, and now it works for them on their own data. This is a major thing to have.
Yeah, like getting a user to be able to fiddle as quickly as possible with the thing. It requires you to get over that initial hurdle, but from there you want them to just goof around and edit, because turning knobs and seeing what moves is also a great way to learn a package. But without a quick start guide, that is super hard.
Yeah. Right? You want them using the package as soon as possible.
I'm curious now, because I've had a discussion with a colleague of mine like a year ago, and I kind of took like a very principled stance here, which was almost like documentation driven development, that maybe should be a thing. Like before writing any actual code, maybe worry about the docs first. And this is a little bit more for paid products, right? So if you're gonna, it needs to be a feature, so you have to be able to explain it very clearly. And if that's going to be hard, then why implement it? Is this something you've played with around with as well, or I can imagine it's a bit the other way around for you, because usually the technical implementation is the hard bit.
Yeah, I can see the value in doing that. That is not something that I do, because usually I start off not knowing what I'm doing, so it's very hard to write the documentation. But if you know what you're doing, I would definitely write the documentation first.
Okay, but there you say something interesting as well. So this feeling of I don't know what I'm doing, like sometimes that can be a bad thing, but it can also be a great thing. And this is something we've discussed a bit earlier as well, and I think it's something you and I both agree on. Would you argue that sometimes it's just kind of fun to play with a data set, being fully aware that you don't know what you're doing, and that kind of sets your mind free as well? Is it like an exercise you've got experience with as well?
Yeah, I think it's important to just play around with ideas and see what happens. And I think not having preconceived notions really helps. There's a great paper that somebody wrote where they handed students a data set with either a preset hypothesis that they were supposed to check for, or just handed them the data set and let them play. And you're grinning, so I assume you know the one. If you plot the data set as a 2D
gorilla
scatter
data
plot,
set.
yeah, it's a gorilla waving at you. And apparently, if you start with a hypothesis of what you're looking for, you don't notice the gorilla. So
the name of the article is "A Hypothesis Can Be a Liability," and it is a great read. It is almost a career-altering experience for me to read that thing, because you do like what I remember from reading that is that suddenly I was able to give myself permission to take playtime seriously, if that makes sense. So sometimes it actually makes sense that you give yourself an hour in the week where that's not really a goal. You're just going to goof around, and then you're going to reflect later. And oftentimes it turns out that there's something about being able to play. You need to give yourself permission for it, but boy, you lose something if you don't. And it's comforting, at least to me, to hear that that's also a philosophy that ended up resulting in stuff like UMAP, kind of more on your end. So that's maybe something more people should do.
Yeah, absolutely. Write some code and play around. That's how half these algorithms I have developed got implemented, was just playing around. Does this idea even work at all? And if so, how do I fix it so it does?
Yeah, and can I get it to work in practice? Because then I can worry about if it works in theory. kind of the other way around, almost.
Oh, yeah. So this is a thing that I don't know if it's a widespread practice, but I and my colleagues where I work definitely work this way regularly. Is we pivot constantly back and forth between theory and practice, because we want a well theoretically justified algorithm, but we also would really like something that works in practice. That's important. And so we talk about it as doing the theory work and then the engineering hill climb work. So you build some theory, and then you implement it, and then you take that implementation and go like, okay, what do I need to change? How can I make this end result be better? And you just do whatever it takes, right? Like you're just fiddling with code at this point. And you end up with something that's better than your theoretical implementation. And now your question is, okay, now what theory do I need to have headed in that direction?
Yeah.
You develop that theory and you end up with something that is different than what your implementation did, but now you implement that and it's better again. And so this pivoting back and forth between trying to do what makes theoretical sense and ensuring that it's something that actually works, and just doing the play to see how can I make this better. That's pivoting back and forth between those two viewpoints is a great way to steadily ratchet your way up.
Yeah, and it kind of prevents you from getting stuck from a local optima in terms of like the way you think. I can imagine that's also kind of a useful thing, because at some point you're in code mode and you kind of go, I got to get this fixed. And then let's go to theory mode. And then you wonder, well, is this the most efficient algorithm? Oh, wait, maybe a data structure. Then you implement the data structure and you go, oh, but the API is just horrid. Let's fix that. And then, oh, but hang on, if we do the change in the API, there's another thing we can use, and et cetera, et cetera, et cetera. Like keep on escaping the local hill, so to say.
Yeah, absolutely.
Cool. Then, yeah, this was a really fun conversation. If people want to, like, we have to wrap up due to time, but if people want to maybe reach out to you, also ask questions about UMAP, I suppose GitHub is still a place where you hang out and you're still at the repositories once in a while.
Yep, I'm around there.
So that'll be a place. Any other, like, are you on social media or not as much?
I exist on Twitter. I don't post a lot.
So, okay, so still around on Twitter, definitely still around on GitHub. Leland, thanks for all your good work in these packages. They are great. I'm definitely eager and looking forward to your KDearestNeighbors stuff. If I can pitch a name, I think KDearestNeighbors will be cool. Not saying you have to use it, but I will say it will be fun. And I'm really looking forward to it, because I do think this whole data as a model, besides being a fun abbreviation, I do think is also just inherently a good idea. It's really sweet to have models that can sort of say, well, I raise a won't predict flag, and I really give you that interpretability. So there's definitely stuff to like there. I'm definitely looking forward to it.
Absolutely. Thank you so much.
Have a good one.
Thanks.